Hi everyone. In this video, we will conclude our discussion of the Riemann-Stieltjes integral by working through 4 examples. Each example will utilize properties of the Riemann-Stieltjes integral that we have previously discussed, but each will have specific areas where we need to take care and pay attention to how things are working in order to make sure we apply those properties properly. The final example will illustrate a non-property of the Riemann-Stieltjes integral. So to begin, let's look at this first example. Let f of x be sine of x, let alpha of x be e to the x, and define both of those on the interval 0 pi. Imagine I want to calculate the Riemann-Stieltjes integral of f with respect to alpha from 0 to pi. Now, recall that in order for the Riemann-Stieltjes integral to be defined, our function f should be bounded. In this case, sine of x is bounded between -1 and 1. And our alpha of x should be monotone increasing. E to the x is, in fact, monotone increasing. So it makes perfectly good sense to talk about the Riemann-Stieltjes integral. And in this particular case, we can actually say even more. F is continuous. Alpha of x is also continuous. And in fact, not only are they both continuous, they're both differentiable, and they're infinitely continuously differentiable. So these are very nice functions. In particular, since this alpha of x is differentiable on the interval from 0 to pi, we can actually calculate this integral by applying an earlier theorem that says the Riemann-Stieltjes integral of f with respect to alpha is the same as the Riemann integral of f times alpha prime, again, provided that this alpha prime is differentiable on the closed interval 0 pi. So we can apply this theorem, and now this has just turned into a Riemann integral type of problem. Now, the nice thing about converting these Riemann-Stieltjes problems into Riemann problems is that you have a whole host of tools for dealing with Riemann integrals, both tools that we've learned in this course, but also an entirety of the calculus sequence, right, that really focus only on Riemann integrals. So in particular, right, if I just write out what this is, this would be the integral from 0 to pi. So my function f is sine of x. My function alpha is e to the x. So alpha prime, the derivative of that, is also e to the x. And so what I get here, right, is just, I'm going to swap these around. I get that I need to evaluate this Riemann integral. Now, this is a Riemann integral and meets all the criteria for applying the fundamental theorem of calculus. So if I think about, color here, if I imagine this is some function little g, I could apply the fundamental theorem of calculus and say, well, this will just be capital G of pi minus capital G of 0, where I'm assuming that capital G is an antiderivative of little g. So now what happens is I've turned this question about a Riemann-Stieltjes integral into a question about a Riemann integral. Because it's a Riemann integral, I've actually been able to turn this into a problem about finding antiderivatives. Calculus 2 primarily is a course all about finding antiderivatives. Now, students in Calc 2 would often tell you that it's a course about integrating, but it's not really about integrating. It's about finding antiderivatives. And then once you have those antiderivatives, you can compute integrals because of the second fundamental theorem because of the fundamental theorem of calculus. So now, in order to find this function capital G, we can just go back and use some Calc 2 tools, right? So I really just want to find an antiderivative of e to the x sine of x dx. Okay. And if you haven't done this in a while, you know, this might be, there's a trick here that maybe you've seen before but might have forgotten. We're just going to integrate twice, integrate by parts twice. and then we'll be able to subtract something over. So let's apply integration by parts. I'm going to let my u be e to the x. My dv will be sine of x dx. So my du will just be e to the x dx. Derivative of e to the x is just e to the x. My v will be the antiderivative of this, so this will be minus cosine of x. And now I apply the integration by parts formula. The integration by parts formula says the integral of u dv is equal to u times v. So I'm going to get a minus e to the x cosine of x minus the integral of v du. So I'm going to get a minus the integral of v, which is minus cosine. So I'm going to bring that minus out, du. So I'm going to get a plus integral e to the x cosine of x dx. Now, if you're just applying integration by parts, you might look at this and say, integration by parts really just swaps out one integral for the other. You hope the other is better. And you look at this and go, well, I don't have any better sense of how to deal with this than I did this. Maybe this was a failure. But it wasn't. So watch, we're going to apply this again. Now, it's important here that before you used u to be your exponential function and v were your trig functions, you need to keep that the same. If you were to swap here, if you were to make u cosine of x and dv e to the x, you would go through this and you would end up at the end with this for the whole expression. Okay. And while this is true, it is true that this is equal to this, it's not helpful, right? So we want to make sure we keep them in the same order so we essentially don't just undo the integration by parts that we just did. So we're going to, this will still be e to the x. My du will be e to the x dx. My dv will be cosine of x dx, and its antiderivative will just be sine of x. All right. Now this first term here is just coming along for the ride. It's e to the x, or sorry, minus e to the x cosine of x. And now I get that this integral is equal to u times v, so e to the x sine of x, minus the integral of v du, so that's going to be minus the integral of e to the x sine of x. Now, again, on the surface, it feels like I've made no progress. I've just sort of gone round and round, and I'm back to the same integral. But now, if we look at this quantity, this is the quantity I'm trying to find, right? And so now I can think of the stuff in this blue box as a variable that I'm trying to solve for, right? So if I were to take an integral of e to the x sine of x and add it to each side here, right? What would happen? Well, over here, adding it would get rid of this one that's subtracted here. Over here, I would now have two of these things. So I'm sort of ignoring this middle part, right, for the time being. Okay. So now I would have that 2 times the integral e to the x sine of x dx is equal to negative e to the x cosine x plus e to the x sine x. And now if I want to find the value of this integral, I just multiply through by 1/2. And I get that the integral of e to the x sine of x dx is equal to negative 1/2 e to the x cosine of x plus 1/2 e to the x sine of x. All right. Well, again, now I've used that sort of Calc 2 trick to help me find the antiderivative. Now, if I come back up here, get rid of this work now. Really, all I need now is the antiderivative that I was able to find. Okay. I guess if this were a Calc 2 course, at some point you should yell at me because I didn't write plus c down here, so I didn't find every antiderivative. But remember that here I don't need every antiderivative. I just need g to be an antiderivative. Okay, so in this case, I can say that this integral from 0 to pi of f d alpha is going to be equal to this function. This is going to be my capital G evaluated at pi. So if I evaluate this at pi, sine of pi is going to be 0. So this whole term will go away. This term, if I plug in pi, cosine of pi is -1. So I'll get a 1/2 e to the pi. That's going to be my g of pi. Minus a g of 0. If I plug in 0, well, sine of 0 is 0, so the second term goes away. This first term, cosine of 0 is 1. E to the 0 is 1. So I'm just going to get a minus 1/2. So I have a minus -1/2. And so there is the value of that Riemann-Stieltjes integral. So again, let me highlight here, in the case that our alpha is differentiable on the closed interval, then we can fairly easily compute these by just turning them into Riemann integrals and using the considerable number of tools we have at our disposal for evaluating Riemann-Stieltjes integrals. Okay. So in the case where alpha is differentiable, these really, they're just Calc 2 type problems, right? We just reformulate it in the appropriate setting in order to turn it into a Riemann integral. Once we do that, we can use the fundamental theorem of calculus. Once we do that, we can use tricks from Calc 2 to find appropriate antiderivatives and evaluate the integral. All right, great. All right, well, that's all well and good, but of course, we deal with more complicated types of alphas. They're not all differentiable. So let's see what happens in some other cases. So let's actually go back to this. This is an example we looked at when we first introduced the Riemann-Stieltjes integral. So we've actually already calculated this. Just to recall, so let f of x, let it be this function, or just let it f be any function, okay, bounded function, okay? But here's one particular example. And when I say bounded, I mean bounded on -1 to 1. So this is bounded on -1 to 1. If I look at this, right, just recall that this function, right, this is really just the function which is 0 when x is less than 0 and 1 when x is greater than or equal to 0. Okay. And so we were actually able in a previous video to calculate this. When we calculated it, we actually found that the value you get is f of 0. For this particular function, it would be 1, right? But you just get f of 0 here. Yeah. Now, what I want to do is I want to actually show you another way of thinking about this problem that has a mistake. And the real key here, what I want you to do is I want you to see if you can find my mistake. Okay. So suppose instead I were to do the following. So we calculated this by thinking about what the upper sums look like, thinking about taking the infimum of those upper sums and concluding that the upper integral was 0, the upper integral was f of 0, the lower integral was f of 0, so the actual value of the integral must be f of 0. But suppose I approach this a different way. So suppose I said, all right, I want to calculate this. Let me break this up. I'm going to rewrite this as the integral from 0 to 1 of f d alpha plus the integral from -1 to 0 of f d alpha plus the integral from 0 to 1 of f d alpha. And well, if I look at this function on on -1 to 0, my function is differentiable. It has the value 0. So I could actually rewrite this f times alpha prime dx. And I could do the same thing over here on the intervals, like on the interval 0 to 1, right? My function is the constant 1, which is differentiable. So I can rewrite it this way. And well, actually, wait, these functions are constant. right? Or sorry, alpha is constant on the interval -1 to 0, so its derivative is just 0. And same over here on the interval 0, 1, alpha is constant. And so that derivative is just 0. And so, well, this is just an integral of 0 plus an integral of 0. Those must add up to be 0. Right? Now, obviously, there's a mistake somewhere, right? F of 0 in this particular case, but in general, like need not be 0, right? And it's not in this particular case. But over here, I'm getting that the value of the integral is 0. Now, we did this from the definition. Okay, we've done this by applying some theorems. Probably we have not carefully applied a theorem over here. And so we want to carefully think about all the steps we've taken and which ones are justified. Okay, so let's see. In this first step, we've applied the algebra of Riemann-Stieltjes integral theorem, okay, which said that if there was a point C between -1 and 1, I could rewrite this in this way. The conditions there were just that F needed to be Riemann integrable with respect to alpha. It is, right? We've already calculated that. In fact, this is continuous, so this Riemann integral should exist. So that's not the problem. This step seems perfectly valid. Okay. We then said that alpha was differentiable on each of these subintervals. Okay. And here is where our mistake first comes in. Okay. In order to apply this theorem that allows me to rewrite a Riemann-Stieltjes integral of f with respect to alpha as a Riemann integral of f times alpha prime, that requires that my function be differentiable on the closed interval. Okay. So what is happening there? So if I actually look at this, right, on the interval from -1 to 0, my function is not actually even continuous on that interval, right? So on that interval, everything is 0 right up until I get to 0. And at 0, my function jumps to 1. So I actually cannot apply this step here. This step is invalid. Now, this step over here actually is valid. On the interval 0, 1, my function is always 1. So this is valid. So I can actually say that this integral is 0. I can't use this line of argument to say that this integral is 0. And in fact, if you go through and calculate it, what you get is that this integral is in fact f of 0. Okay. So what I want to sort of emphasize through this example is we have to be very careful when we're applying those sort of algebraic properties of Riemann-Stieltjes integrals to make sure that we're not neglecting endpoints of things. Often if you have alphas that are sort of jumping around, you need to be careful, alphas that have jumps in them, you need to be careful about exactly where they're continuous and differentiable on a closed interval versus an open interval, right? Those things can all matter. So when I set up here, oh, alpha is differentiable on the interval -1 to 0, I didn't really specify whether that was the open interval or the closed interval, right? And so I have to be really careful about these kinds of things when I'm dealing with these alphas, especially if those alphas are discontinuous, right? And so near those points of discontinuity, I need to take a little bit of care. So again, these properties are all very, very helpful, but we do have to be very careful about the ways in which we apply them and make sure that all the necessary hypotheses are met before we just start applying them and it actually turns out that we haven't applied them properly. All right. For this third example, I want to look at the integral of, so I'm just going to take my function f of x to be x. And now the alpha of x that I want to look at is x squared plus floor of x. And I'm going to look at all of these functions on the interval from 0 to 2. And I want to calculate this integral from 0 to 2 of f d alpha. Okay. Well, in this case, the alpha is a sum of two functions. Now, since my function f is continuous, it will be integrable with respect to x and with respect to floor of x. So I know that f is Riemann integrable with respect to each piece here. And therefore, I can apply one of my properties of Riemann-Stieltjes integration, which says I can break up the integral over a sum in the integrator. Now, again, it's also important to make sure, right, each of these, right, are themselves monotone increasing. So I can rewrite this as the integral of f dx plus an integral from 0 to 2 of f d floor of x. Now notice this first integral here, right, this is just, oh, sorry, x squared, right? So notice that, again, x squared is monotone increasing on 0, 2. So sorry, I missed that. It's x squared, but it is still integrable. Sorry, it is still monotone increasing on 0, 2. So these Riemann-Stieltjes integrals all make sense. So here, notice that this f with respect to x squared is differentiable on this interval. Okay, so I can actually apply this is f times the derivative with respect to x of x squared dx. Okay, so here, since this is differentiable, I can use my theorem about having a differentiable integrator to evaluate this. Here, I have to do something a little bit different. Okay, so let me actually just leave this as is for a second. Let's deal with this. This first piece will be, so the derivative of x squared with respect to x is 2x, f is x, so this is 2 times x squared dx plus this other integral over here, 0 to 2 of f d floor of x. All right, so what is this? Antiderivative of x squared is x cubed over 3. So this would be 2 times 2 cubed over 3 minus 0 cubed over 3 plus this other integral, which again, we're going to deal with momentarily. This first piece, though, what do I end up with? This is 8. 8 times 2 more is 16, 16 thirds. Now we have this other piece we have to take care of. Now, what I want to do here is really understand how do we integrate things with respect to these sorts of step functions. So we saw in example 1, right? In example 1, we were looking at that sort of step function that just goes from 0 to 1, and it goes from 0 to 1 at x is equal to 0. And what happens is where we took that step of size 1, all our integral did was pick up the function value there. Now, if we think about plotting, so let's say here's the interval from 0, 0, 1, 2, 3. And let's say I want to plot this step function here. So what does this do? This floor function, and you can also think of it as the round down function. So for any input between 0 and 1, it's going to round down to 0. Okay. Except at 1, because 1, right, is a whole number, and anything above 1 up to 2 will round down to 1. And then once you get to 2, right, you're at 2. And anything between 2 and 3 is going to round down to 2 until you get to 3. And then anything right there. So this function sort of looks like this. Okay. And what you notice is uh, you have these functions alpha, which are piecewise constant. And what's going to happen is you're actually just going to pick up the step size times the function value at each of these jumps. Okay. Now, to see why that's true, so imagine we're trying to integrate from 0 to 2 with respect to this function. So I have some partition. So imagine I have some partition here. So I'm plotting my x here, and these are the x's in my partition. Okay, so 0 has to be in there, 2 has to be in there, and then there's some other things in here. Now think about my delta alpha k's. On most of these subintervals, my delta alpha k is going to be 0. So as I'm calculating like something like an upper sum, okay, many of these terms are going to be 0. The only ones that aren't going to be 0 are the intervals that contain the jumps. Okay, so notice there's a jump at 1, and there's also a jump here at 2, right? Because right at 2, I'm integrating from 0 to 2. So if I just restricted this function to 0, 2, my function looks like this, right? But note that I do still have a jump here, right? So the only things that are going to survive here, I'm going to end up with like an capital M sub I times delta alpha I plus like an M sub n delta alpha n, where the ith interval is the one that contains 1, and the nth interval is the last one, right? It contains this jump. Now, in those cases, these jumps here are size 1. So the difference between your alphas is just going to be 1. So you're going to get an M sub I plus a M sub n. This is like an upper sum. Okay. And then to find the upper integral, you want to take the infimum of all these. Well, the way you make these smaller, because these are each defined to be supremums over these subintervals, is you make the subinterval smaller. Okay. Well, as you make the subinterval that contains 1 smaller and smaller and smaller, what's happening? It's collapsing to f of 1. And same thing over here, as you make this subinterval that contains 2 smaller and smaller and smaller, it's just collapsing to 2. And so your maximum is just going to be f of 2. So you get here that like the infimum of pf alpha, basically the smallest this could be over any partition is f of 1. The smallest this could be over any partition is f of 2. So you have here, right, this infimum is your upper Riemann-Stieltjes sum. Now, again, I know that this is Riemann-Stieltjes integrable because f is nice and continuous. So this upper integral must be actually the value of the integral itself. So this turns out to just be 16 over 3 plus f of 1. And f of 1 is just going to be 1 plus f of 2, right? F of 2 is just going to be 2. So this is equal to 16 over 3 plus 3, or plus 9/3, which is 25/3. So what I want you to see in this example, right, we've sort of carefully applied this sum of integrators property. But also, when I have step functions, right, if I integrate something with respect to a step function like this, what I always get out is the function value where the step occurs, so f of 1, and I actually get it, it's a little hard to see here, I get it times the height of the step. It's hard to see that that happened here because the step is just 1. But right, I have this delta alpha k here, right? In this case, the delta alpha k over this subinterval that contains 1 is just 1. Okay, but if these steps had been spaced further apart, right, if the jump here went up 3 and then the next one went up 2, I'd have a 3 and a 2 here. right? And so I'd have a 3 and a 2 here. So what you end up with here are just the function values where the steps occur times the height of the step. Now, again, this only works assuming you have flat steps. So you have piecewise constant steps, all right? But if you do, then you can calculate, you use exactly the same ideas to calculate those exact Riemann-Stieltjes integrals, and they just come out as some linear combination of the function values. All right. Now, in our last example, we are going to look at a non-property of Riemann-Stieltjes integrals. Okay, and we're actually going to do it. We're just actually going to look at Riemann integrals, but remember those are a special case of Riemann-Stieltjes integrals. So if I can show that something doesn't hold for Riemann integrals, then that certainly means it can't hold for Riemann-Stieltjes integrals as well, because Riemann integrals are a type of Riemann-Stieltjes integral. All right. So before we look at the particular example, right, really a lot of mathematics boils down to I have, thing one has property X, thing two has property X. I combine them in some natural mathematical way, and I want to know if their combination has that same property X. So think about all the like algebra of whatever theorems, right? So I have a function which is continuous. I have a function f which is continuous at 2. I have a function g which is continuous at 2. Is f plus g continuous at 2? Yes, right? I've taken two things. They both have this property, continuity at 2. I've combined them in this appropriate mathematical way, addition of the functions, and I see that I actually get a result which also inherits the same property that the individual components had. Right? And this happens in like so many different ways, right? And way out of analysis, right? So if I take a group G1 and a group G2 that are both commutative, and then I take some sort of product of those groups, right? Does that resulting thing, is it a group and is it commutative? Right? So this happens all over mathematics. So what I want to sort of think about, imagine I have a function that's Riemann integrable, and then I have another function that's Riemann integrable. So I have two functions that are Riemann integrable. Now, we've already proven that their sum, their difference, their products, like we've talked about, all those things must be Riemann integrable. But what about their composition? Okay. Well, let's look at the following example. So take f to be the function which is 1 at 0 and 0 everywhere else. And take the function g. Now, we've actually seen this function g before. This function g is what we referred to as Thomae's function back when we were looking at issues of continuity. So we saw, for example, that this function is continuous at every irrational value and not continuous at every rational value, okay? But this function is defined, so if you have an input x which is rational, right, and you express it in terms p over q in lowest terms, then this just returns 1 over q. If the number is irrational, it returns 0. Now, I want to see if I can calculate the integral from 0 to 1 of f composed with g. Now, this function, it's actually fairly straightforward to show that this is Riemann integrable. So if you compute, say, an upper sum, so the idea would be, and again, we're just looking at Riemann integrals here. So if I compute an upper sum of f over some partition, that would be a sum k equals 1 to n of m sub k delta xk. Most of these m sub k's, right, on every partition that doesn't contain 0, you're going to get 0 because the function is going to be constant. Okay, so most of these end up being 0. It's possible that if you have a partition value right at 0, that you get two subintervals where the maximum is both 1, right? So if you have a partition value at 0, then the subinterval to the left, the maximum over that is 1, and the one to the right, the maximum is 1. Because again, both of those subintervals will contain 0. So worst case scenario, you end up with a delta xi plus a delta xi plus 1. Okay. And the maximum on that interval is just going to be 1, because that's the maximum value of the function. And so you get this for your upper sum. And then you ask, well, what's the smallest if I take the infimums over all partitions? What's the smallest this could be? Well, you can keep taking your partition to have smaller and smaller intervals around 0. So this infimum actually is 0, right? You can basically keep shrinking those so that they approach 0. So this tells you that the upper Riemann integral, in this case from 0 to 1 of f dx is actually equal to 0. The lower integral is also 0. Okay, no problem. Actually, and now that I'm looking at this, being a little more careful about this, if we're looking on the interval 0, 1, you're only going to get 1, right? Because you're only going to pick up the one that contains 0, and that's going to be the first one. So actually, you just get delta x sub 1 there, right? So if I'm integrating this on the interval 0, 1, it's 1 at 0 and then 0 everywhere else. Okay, but this is Riemann integrable. The Riemann integral is 0. Okay, now G is also Riemann integrable. We could prove this right now. It would be a bit tricky. Okay, and the reason it would be a bit tricky, we'd have to do some very careful estimations with upper and lower sums. It actually turns out that if you go on to take Math 5620, Analysis 2, we will come up with something called the Lebesgue criteria for Riemann integrability, which actually makes proving this is Riemann integral really easy. Now, let me give you the idea. The idea is that the places where this function is not continuous, right? Places where this is not continuous are the rational numbers. And in the interval 0, 1, and in fact on any interval, those are a very small set in some appropriate sense. Now that appropriate sense is going to be in the sense that it has something we'll call Lebesgue measure 0. But so we will be able to show later on that this is also Riemann integrable. Okay, for now, let's just take as given the fact that these are both Riemann integrable. Well, now let's look at the composition. If we want to try and integrate the composition, right, I should ask myself, what is that composition? Okay, so what is f composed with g of some value x? Okay, well, it's going to go first into the function g. So we better break it up. So what if x is rational? So if x is rational, I'm going to look at it in lowest terms, and it's g of x is going to be 1 over q for some value of q. Now I'm going to take that value and I'm going to plug it into my function f, right? So I've taken my number x, I've gotten g of x, which is 1 over q, and now I'm going to plug g of x into f. So I plug 1 over q in here. Well, 1 over q is not 0, right? So I will get back 0. So when I take a rational number, plug it into G, take its output, plug it into F, I always get 0 back. Okay. What if I take an irrational number? Well, if I take an irrational number, G is going to give me out 0. Now I take that and plug it into F. F of 0 is 1. So I get this function, when I take the composition, I get this function which is 0 if x is rational and 1 if x is irrational. Now this looks similar to the indicator function of the rationals, but it's not quite that. This is actually the indicator function of the irrationals. So one way to write the irrationals is just the real numbers delete the rational numbers. So this is actually the indicator function of the irrationals. Now, we actually proved that the indicator function of the rationals is not Riemann integrable. What about this? Well, let me observe one thing. The indicator function of the rationals can be written as 1 minus the indicator function of the irrationals. Think of it this way. If I take and were to plug in a rational number here, so if I were to plug in a rational number for my x, what would happen? I get 1 minus, if I plug in a rational number here, I get 0. So what would happen is if x is rational, I would get 1 minus 0, because I get 0 out of this function, which would be 1. If I plugged in an irrational number here, right, I'd get 1 minus, plugging in an irrational number here would give me 1. 1 minus 1 would be 0. So what would happen then if this was integrable? Then the indicator function of the rationals would be integrable function, that's just a constant function, minus an integrable function. So if this function were integrable, then the indicator function of the rationals would be integrable. But we know it's not. So this must not be integrable. Okay? So we can actually say here, I asked you to calculate this, but f composed with g is not Riemann integrable. So what this example illustrates is that it is possible to take two Riemann integrable functions, take their composition, but you get back a function which is not Riemann integrable. So Riemann integrability is not a property that is preserved by composition of functions. Okay. Now, typically when we see something like this, we start to say, okay, well, could I strengthen the requirements? Maybe I need something a little more than Riemann integrability, right? Certainly I know, for example, if I take two continuous functions and compose them, I get another continuous function. And a continuous function is always Riemann integrable. So maybe I need to somehow build in some continuity here in order to get a Riemann integrable function out. And that intuition would be entirely correct. The interesting question then is sort of, well, how much integrability do you need and where do you need it, right? Do you need f to be continuous? Do you need g to be continuous? Do you need them both to be continuous? Like, what do you need in order to ensure that the resulting composition is in fact Riemann integrable? But again, you want to do that. Certainly you could say if f and g are both continuous, then their composition will be Riemann integrable because their composition will be continuous. That seems like overkill. So is there some happy medium in between? And so the last thing I just want to show you is actually this theorem. We're not going to prove it, but it actually turns out that composition will preserve integrability if one of your functions is continuous. So be a little careful here because they've actually swapped the roles of f and g from the way the book swaps them from the way I did it earlier. So just think in terms of inside and outside functions. So your inside function here is f and your outside function is g. What this says is, suppose your inside function is Riemann-Stieltjes integrable and bounded, and suppose g is continuous. So the idea here is if you take a continuous function and compose it with a Riemann-Stieltjes integrable function, then you will get back a Riemann-Stieltjes integrable function. So outside function needs to be continuous, inside function just needs to be Riemann-Stieltjes integrable. Then that composition will result in a Riemann-Stieltjes integrable function. Okay. So again, some of these things work really well. Sum of two Riemann-Stieltjes integrable functions is Riemann-Stieltjes integrable. Other things like composition we see in this case. The composition of two Riemann-Stieltjes integrable functions is not necessarily Riemann-Stieltjes integrable. So we do have to be careful as we apply this property and all of the other properties that we've learned about Riemann-Stieltjes integration.